In this video, I'm going to do one more example of calculating a probability using complementary events. And in this example, the two events that are in question are going to be dependent events. 7 women and 3 men are in a group. If 3 people are chosen at random, what is the probability that at least one is a man? Again, as in the last video, you notice that these words "at least" signal for us that potentially using complementary events is going to be an easier approach to solve this problem. The first step always in these problems are to actually list your 2 complementary events. One of the events is always going to be given to you. It's the condition in the problem. So I'm going to call that event A, and event A is going to be at least one man. That would obviously include the cases where there was 1 man chosen, or 2 men chosen, or all 3 men chosen. It's going to be difficult to calculate that probability. So our strategy is going to be to calculate the probability of the complement, which we're hoping will prove to be easier. The first thing we have to do is we have to identify what is the complementary event in this case. If A is at least 1 man, the opposite of that, or all other cases in the sample space, would be no men chosen. If A and B are complementary events, and in this case we've chosen them so that they are, we know with 100% confidence that the probability of A plus the probability of B will be equal to 1. Since we don't want to calculate the probability of A because of its difficulty, we're going to rearrange this equation and say we can figure out what the probability of A is by finding the probability of B. So I'm going to subtract the probability of B from both sides, and this is ultimately the equation that we're going to use to solve the problem. So what we want to do is we do need to find the probability of B, the probability that no men are chosen. But the problem is, when a person is chosen from the group, and then you go back to choose the second person, those events right there that are happening are dependent on one another. Let's explain what I mean. So when the first person is chosen, in order for no men to be chosen, the only way that that can happen is if we have no man, and no man. Or an easier way to think of that would be, instead of considering this to be no man, just think of it as the probability that a woman is chosen, another woman is chosen, and a third woman is chosen. Now, the difficulty we're going to run into here is that each time a person is chosen, they're removed from the group, and they're not returned to the group. So that means that from the first choosing to the second, those are dependent events. What do I mean by that? Well, when the first woman is chosen, the probability that that will happen is 7 out of 10. Why? Because there's 7 women in the group out of a total of 10 people. But once that woman is chosen, now when the second person is chosen, we only have 9 people to choose from. And since we assumed that the first person that was chosen was a woman, we now only have 6 women to choose from. So the probability that the second time the woman is chosen is not again 7 out of 10, but instead it's 6 out of 9. You can probably pick up on the pretty easy pattern that's occurring here. The probability that the third woman will be chosen is 5 out of 8. There's now only 8 people and there's only 5 women. Notice the numerator is decreasing by 1, the denominator is decreasing by 1 each time. So altogether, this is the probability that a woman, and another woman will be chosen, or in the way we stated it, the probability that no men will be chosen. When you multiply this out, and I'm going to put this in decimal form, this probability rounded to the nearest 100th is 0.29. So if the probability that no men are chosen is 0.29, we're just one step away from finding the probability that we really care about, the probability that at least 1 man is chosen. Using this formula down here, the probability of A, which is what we want, is 1 minus the probability of B, but that's what we just calculated. The probability of B is this 0.29. When we do that subtraction, we end up with the probability of A being 0.71. So to answer our initial question, the probability that at least 1 man is chosen is 0.71, or 71%.